So as I've been telling you guys in class, there's a lot of trig stuff that was not included in the Common Core curriculum, and this is going to be one of them, the trig identities. One of the most common is the Pythagorean identity, which you can see listed here, sine squared plus cosine squared equals 1, and that's coming from Pythagorean theorem. So Pythagorean theorem says that a squared plus b squared equals c squared, but if we're on the unit circle, our c squared is 1 squared, our x and our y, or our a and our b, are cosine and sine. So that's where this equation is coming from. Oh, didn't fit that in very well. Now, in number 1, we're kind of going back to something a little more simple, but it says the angle theta has its terminal ray in the second quadrant. So let's draw a picture of a triangle in the second quadrant. And remember, your reference triangles always have to go back to the x-axis. So it has to look like that. And if they're giving you sine, they're giving you opposite and hypotenuse. Now you can easily find that missing side by doing Pythagorean theorem. If you want to do that now, you can. I'm going to tell you that that side is 12. So now the question wants to have you find the value of cosine theta. Well, cosine is adjacent over hypotenuse, so the value is 12 over 13, but we need to remember, are all students take calculus? We're in the S quadrant, where only sine and cosecant would be positive. We're not doing sine or cosecant, so our answer would be negative. Okay. Now, not every angle will work out nicely when we're finding the sine or cosine of it. For example, we know sine 120, we know sine 135. Anything that has a nice reference angle of 30 or 45, we can find the sine, cosine, tangent, etc. of. But what if we get something like sine of 75? If I drew a 75-degree angle on my axes, this is going too far. If I drew a 75-degree angle, it would be in the first quadrant, but it would have a really ugly reference angle. So we have to figure out a way that we can figure out sine 75 using our quote-unquote nice angles. And I'll kind of write these over here, our quote-unquote nice angles. Like I said before, anything that's a multiple of 30, that'll be a nice angle because it'll have a nice reference angle. But also, anything that's a multiple of 45 will be a quote-unquote nice angle. Okay. So we have to use those to figure out how to get 75. Well, one of the easiest ones that I see is 30 plus 45. So sine 75, we can rewrite as sine 30 plus 45, which matches up with this formula here. Instead of A, we have 30, so sine of 30. Instead of B, we have 45, so cosine 45, plus sine 45, cosine 30. Now hopefully you guys remember your special right triangles that we did learn during the year. If we think about sine of 30 degrees, or cosine of 30 degrees, here's my 30-degree angle. Opposite that is a half. Hypotenuse is 1. Adjacent to that is square root of 3 over 2. So sine, which is your y value of 30 degrees, is positive 1/2. Cosine of 30 degrees, which is your x value, is square root of 3 over 2. Then you would do the same thing to find cosine 45 and sine 45. Both of those end up being square root of 2 over 2. So you get square root of 2 over 4 plus square root of 6 over 4, which we can't combine those. They're not like terms. So all we can do is write them over the same denominator. Okay. Similarly, in number 3, we want to find cosine 15. Well, that's going to require us to still use 45 and 30, but now we have to do cosine of 45 degrees minus 30 degrees to get 15 degrees. Okay. So now this is matching up with this formula here, cosine of a minus b. So let's match that up with what it's equal to. Cosine of a, cosine 45, cosine of b, cosine 30, plus sine of a, sine of b. And we already found all these values up above. Cosine 45 was square root of 2 over 2. Sine 45 was square root of 2 over 2. Cosine 30 was square root of 3 over 2. And sine 30 was 1/2. Okay. So when we figure this out, again, we get square root of 6 here, plus square root of 2, and they're both over 4. Okay. So pretty easy so far. Let's look at number 4 on the back. So now it says for two angles, alpha and beta, it is known that alpha is between 0 and 90, so alpha is in the first quadrant. Beta is between 90 and 180, so that's in the second quadrant. And then they give you cosine alpha, mine looks like a negative, but that's an equal sign, and sine beta. Find the following values in simplest form. Find sine of alpha. Well, if we know what cosine alpha is, and we know alpha is in the first quadrant, we can draw a picture in the first quadrant. Here's our angle alpha. Cosine is adjacent over hypotenuse. Well, if we do Pythagorean theorem, that missing side is going to be 4. So sine of this angle, opposite over hypotenuse, would be 4/5. And we don't have to worry about any negatives here because we're in the first quadrant where everything is positive. Okay. Similarly, we can find cosine of beta. Draw a picture in the second quadrant. Here's my angle beta. We were given sine of beta, so opposite over hypotenuse. If you do Pythagorean theorem for this problem, the missing side ends up being 24. So now we want cosine, which is adjacent over hypotenuse, 24 over 25. But now that we've left the first quadrant, we have to figure out whether that's positive or negative. And in this case, it'll be negative. Now, sine of alpha minus beta. Well, check out the formula for sine of a minus b. Sine of a, which in this case is alpha, cosine of b, which is beta, minus sine of b, cosine of a. Let's start plugging in. Sine of alpha, let's see, sine alpha we found up here, 4/5. Cosine beta we found in part B, negative 24/25. Sine beta was in the problem, 7/25. So was cosine alpha, 3/5. Now, don't try to be a hero at this point. Fractions are probably not your strong suit. Make sure you use your calculator to help you out a little bit here. Negative 117 over 125 is your answer. Okay. Same type of thing for cosine of alpha plus beta, just a different formula we're going to have to use. This is going to be cosine alpha cosine beta minus sine alpha sine beta. When we start to plug in, cosine alpha is 3/5. Cosine beta is negative 24/25. Once we know all the values, it's easy. We're just plugging in. Sine alpha is 4/5. And sine beta is 7/25. Again, use your calculator to get negative 4/5. Now the next two are a little trickier. And what they kind of want you to do on this sheet, because we don't actually know this formula yet, is to think of sine 2 alpha as sine of alpha plus alpha, because that would be 2 alpha, right? So you could do the problem that way. There's actually a lot easier way to do this. If you take a peek at your reference sheet, which is in the beginning of the packet that you guys have on the very first page in the inside cover, there is a formula for sine 2a, and it says 2 sine A cosine A. And we're kind of skipping ahead here because that's not really the way they want us to do the problem at this point, but it's going to be much easier. So instead of A, though, ours are alphas. Well, sine alpha is 4/5. Cosine alpha is 3/5. I'm going to take this 2 and make it 2 over 1. So we get 2 times 4, 8 times 3, 24 over 25. But again, if you don't trust yourself to not make a mistake there, I would use your calculator at that point. Now there's also formulas for cosine to beta. Let's see, I have my reference sheet up here. Problem here is there are 3 different formulas for cosine to beta. This should all be minus signs. It's really up to you which one you want to pick. I probably would shy away from this one because I'd rather not have to use 2 trig functions if I could just use 1. So I don't know, I'm going to pick the 2 cosine squared minus 1. You could obviously use any of the 3 because we know all those values at this point, but it's just really up to you. So this would be 2 cosine squared beta minus 1. 2 blank squared minus 1. Well, cosine beta was negative 24 over 25. Again, I would probably not trust yourself to do this by hand without making a mistake. So put in your calculator and you get this. Number 5, which of the following is equivalent to this? Take a look at that equation and take a look at your formulas that you have and see what that matches up with. It's going cosine cosine plus sine sine. Cosine cosine plus sine sine. Oh, computer's still going here. Plus sine sine. So if we go back to our reference sheet, cosine cosine plus sine sine is going to be cosine of a minus b, and again my signs are all missing here, but cosine a minus b goes cosine cosine plus sine sine. So I know that this stuff is equal to cosine a minus b. So let's go back. So that's equal to cosine a minus b. Well, in this case, our a is 100, our b is 20, so this is the same as cosine 80. Now, if this was the Regents and you had no idea how to do this, plug this in your calculator in degree mode, plug in all the choices, see which one matches. No reason to get a multiple choice question like this wrong. Same goes for number 6. Worst case, plug that in your calculator, plug all the choices in. Only one is going to give you the same answer, but there's a reason for that. Sine of 70 could be written as sine of 80 minus 10, right? 80 minus 10 is still 70. And if we use our formula for sine of a minus b, that would end up looking like choice 2. We also could write 70 degrees as 40 degrees plus 30 degrees. And if we do that, we'll end up having something that looks like choice 3. We also could write sine 70 as sine of 60 plus 10, which would end up looking like, wouldn't look like choice 4, because sine of 60 plus 10 would go sine 60 cosine 10 plus sine 10 cosine 60. So there's our error right there. Choice 4 is going to be the one that is not equivalent. But again, if you plugged this in the calculator and all that in the calculator, you would get 2 completely different answers. Okay? So that's kind of the basics behind our trig identities for the first day. Tomorrow we're going to do some more work on the next lesson. We're going to do some more work with the double angles and some of the other trig identities. But this is the basics of the sum and difference identities, and we kind of got into the double angles a little bit as well.